Is this on? Okay. Kevin, how are you? Good. I think we're ready to go ahead and get started. We'd like to welcome you to breakout session, Top Applied Research Projects. We're excited to hear from three of our presenters here, and where we're going to be highlighting three research projects that we feel are representative of the top quality research that we're having done in UDOT, and very representative of the innovative and high quality vision that we have as a department as a whole. So just to start off, we've got two sign-up sheets. We'll start one on this side, one on this side. You're able to get one continuing education unit for this presentation. And we also have some certificates up here for those of you that need credit out of state, that if you want to come up afterwards, we can have one of the presenters sign that to give you a certificate for your attendance here at this presentation. I'd like to go ahead and introduce our presenters. First, we will hear from Aaron Smith regarding his research investigating the correlation of laboratory and field friction measurements with regards to bituminous surface aggregates. Aaron Smith is a PhD candidate studying at Brigham Young University and is currently working as a materials engineer for Rabbi-Kistner on the I-15 Point project. He is an ACI instructor and examiner, and also a member of the Transportation Research Board Committee on characteristics of asphalt aggregate combinations to meet surface requirements. His research interests are focused primarily on pavement, friction, testing, and evaluation. Second, we will hear from Dr. Kevin Franke regarding his research investigating the probabilistic liquefaction and lateral spread hazard mapping for Utah County. Dr. Kevin Franke is an assistant professor of civil engineering at Brigham Young University. His areas of expertise include geotechnical engineering, earthquake engineering, foundations, slope stability, and remote sensing through the use of unmanned aerial vehicles or drones. Prior to his current academic appointment, Dr. Franke worked for 6 years as a consulting geotechnical engineer for Kleinfelder and later for URS Corporation. Last, we will hear from Kevin Van Frank regarding his research investigating cold-in-place recycling, sampling, and testing protocol development. Kevin Van Frank is a graduate of civil engineering from the University of Utah and is currently working as a senior engineer at the CME Transportation Group. He formerly worked at Salt Lake City Corporation and more recently at UDOT as an engineer for asphalt materials. He has an interest in the science behind asphalt materials and is currently affiliated with the expert task groups on emulsions, asphalt binders, and asphalt mixes, as well as the subcommittee on materials, section 2C. So we'd like to go ahead and turn the time over to Aaron Smith, and if we can give him a welcome to with a round of applause, appreciate it.
All right. Thank you, Tom. So the topic that we'll be talking about today is pavement friction, and specifically how to correlate, and is there a correlation between the laboratory friction tests that UDOT performs and the field friction tests that they perform. Appreciate Tom, and it's a pleasure to be with you this morning. First, I'd like to acknowledge UDOT. First of all, for their funding. This research project was sponsored through the UTRAC research program that they have. But I also want to appreciate UDOT for their willingness to even look into their friction management program and what they do. A lot of states aren't willing to proactively manage the existing program that they have, and they're not even willing to share information with researchers. So I particularly appreciate UDOT for being willing to look into this and and to share their resources and the data that they have about their current friction program. I'd also like to acknowledge BYU for their help and assistance with this. This presentation, I'll go over an introduction briefly to how the federal government has established a friction guideline for all the states to use. I'll give you some background into UDOT's current approach, where they're at, and where it came from. And then the objectives of this research project, the results, and a brief conclusion on where we can go with the knowledge that we now have from this research. So how does UDOT currently test friction on their roads? We all know that friction is important, and it correlates to safety. It lowers the amount of lane departures during severe accidents. Currently, UDOT has two approaches. In the laboratory, before the asphalt is placed, they have a pre-qualification where the aggregates are tested in an accelerated polish test. And the aggregates have to have a value equal to or greater than 31 to even be used on pavement roads. And then after the roads are placed, UDOT has a network level system to investigate friction. They have a skid trailer that drives around all the state roads and at 1 mile intervals collects friction data. And they have this database. And typically the value is if anything is less than 35, you need to either put signs that say slippery when wet, or you need to take care of it. Put a new surface treatment on it, high friction surface treatment, something to improve the friction. If it's greater than 35, it can remain in place. And so this is where we're at right now. And with this data, we're able to create maps that look similar to this, where you have the good spots in green and the lower friction spots in red. And these are spots that were taken at 1 mile intervals by the skid friction trailer. And this kind of shows you the condition of our existing roads. But you'd think that with such a good program where we try to pre-qualify and predict what the aggregates are going to do in the laboratory, that why would you still have hot spots like this? And can we prevent this? Is this just natural, or is there something more that we can do? So the research that we have will kind of dive into where we're at. So where did this current program come from? It started back in, it's been going on for many years in UDOT, but specifically back in 1996, there was a research report that came out to try to develop some of these target trigger levels on what, should it be 31, should it be 30, what should the laboratory specification target value be, and what should the field friction value be. So in 1996, they studied 32 different chip seal projects, and they took this lock wheel skid trailer that you can see right here. UDOT has a trailer just like this, and what it does is it sprays water, as you can see, right in front of the wheel, and every mile it locks the driver's side wheel up, and it skids it for about 1 second at 40 miles an hour, which is about 80 feet over the outside lane of the road. And so they did this same test on these 32 different chip seal projects throughout the state on pavements that were around 1 to 8 years old. In addition to the field testing, they also performed laboratory testing. And this picture of this red device with the wheel in the middle, this is your accelerated polish machine. And it has the ability, what you do is you take the aggregates that you're going to use and you build coupons, as you can see on the left, and then you subject them to an aggressive polishing cycle where you supply water and some carbide grit into this wheel as it rotates around with a rubber tire, putting pressure on it. And you rotate it for 10 hours. After that, it's similar to what you would find in a rock polishing machine. You throw your aggregates in with their rough edges. When they come out, they're smoother and more polished. And this is an end-of-life type aggressive laboratory test. It would show you what's the worst case condition that your aggregates that you're using on your roads could polish to. So from this, they were able to create a plot. This came from the 1996 UDOT report after they studied these 32 chip seal projects. And they found that in the laboratory, none of their polish values went below 31. And then they set a trigger value for skid resistance out in the field down to about 35. So when we looked at this, and so this is the basis of the existing friction management program. But when we looked at this, we thought, is this statistically adequate? Is this defendable? Can we improve upon it? Should there be a correlation, a stronger correlation between the lock wheel skid resistance out in the field and the laboratory test that's polishing these aggregates? And we felt we could improve upon it and to create a more robust, statistically adequate program. So the research is going to use all of these different devices. One we haven't talked about yet is the British pendulum. That's kind of the bridge between the field and the lab. The British pendulum is a device that was developed over in Europe about 60 years ago. It's small, it's portable, it's lightweight. Typically, you can see it at sometimes accidents on the roads. The police might bring it out to check the friction of the surfaces to see what was it like before the accident occurred. But mostly it's used in laboratories. And after those coupons from the accelerated polish test are finished, they're actually struck with this pendulum. It swings down, it has a little rubber pad on the foot, and it strikes across a 3-inch surface of the coupons. And it's able to measure the friction value of those coupons. Now, because it can be both used in the laboratory and the field, it's a great device. And so what we did before we even started this project is we found all the British pendulums in the state of Utah, brought them together, had a round robin, and we made sure that all the British pendulums were reading about the same. We had coupons that we moved from each pendulum, and we made sure that they were all in line and correlating with each other. And then we felt confident that we could use the one pendulum that we had out in the field when we did our research. So what were some of the objectives that we had for our research project? We wanted to study the field. We wanted to see and observe the skid trailer that UDOT uses. How does it perform? How reliable is it? How repeatable is it? So we were able to go out in the field, and normally you just take one test every mile, but we wanted to do kind of a racetrack style. So we would skid one section, we'd loop back around, skid the exact same section, the exact same wheel path, start and trigger at the exact same time, because you're able to control when you start skidding. And so we were able to do this repeatedly, racetrack style, until we got 4 consistent readings on the pavement. And then we felt confident that we had a true value of what the friction was out in the field. And then we wanted to take this number, we wanted to correlate it to the British pendulum. So we took the British pendulum out to the field, to the exact same spot where the skid test had gone through, and we tested the pavement out in the field with the pendulum. We wanted to get a correlation between these two. The second objective was looking at the British pendulum and the laboratory coupons that were made from the accelerated polish machine. And so we took that same pendulum from the field back into the laboratory, and we struck coupons made from the same aggregates as the pavements that were out in the field. We wanted to see what correlation could we find between those two. And finally, we wanted to see, is there a correlation between the polish value and in the field, the friction from the skid trailer. This was the objective of the research project, and this is kind of the scope that you can see here. There's a problem, though. The laboratory coupons, as you can see, they're curved, they're rounded, but the pavement outside is flat. So how can we bridge the gap between these curved and flat coupons? So we came up with an idea. We created some custom molds that were 7 inches long, that were rounded, similar to the curved coupons on for the accelerated polish machine. We polished the aggregates after we made them, and then we struck them, the curved coupons, with the British pendulum, and then we put these same coupons into the oven. The epoxy softened, we were able to apply pressure to the coupons, flatten them out, and then we restruck them with the same pendulum, with the idea that we wanted to find out what strike path on a flat surface correlates to this 3-inch strike path on a round surface. And we were able to find that about a 3 7/8 inch strike path on a flat surface correlated to the 3-inch curved surface. And now that we had this data, we created a little ruler that had 3 7/8 inch marks, as you can see here, and we were able to go out in the field and start the research. So we picked 12 locations throughout Utah. 5 of them were in Region 2 and 7 of them were in Region 4. We tried to pick the oldest pavements possible that we could find. We sat down with Lonnie Marchant in Region 2 and Mike Miles and identified the oldest pavements. The reason being is because the laboratory accelerated polish test is end-of-life terminal, the worst-case scenario, we felt we'd get the best correlations if we could find the oldest roads that were in service. And so we found that we've got many of our roads that were 10 years old, but in the middle of the research, one of the roads was paved, so it was a brand new road, but we were able to study that anyway. We had 1 chip seal, 5 open grade surface courses, and 6 SMA surfaces. The primary data that we collected were from the skid trailer. We got a friction number, FN, a polish value. This came from the laboratory testing of the coupons. A British pendulum number. We also performed a sand patch test. I don't know if you're familiar with that, but it's where you can figure out the mean texture depth We also checked the air temperature, the tire temperature, pavement temperature, and the tire pressure to make sure that these were consistent through all of our readings. The testing protocol consists of taking 3 British pendulum tests in the red boxes. Two of them would be in the exact same locations where the green skid path went through. And then we also took a 3rd British pendulum test in the middle of the wheel path, just to see is there a difference between where the wheels travel the most and where it's untraveled, and just to see if we kind of see how much deterioration had occurred between the wheel path and the center. We performed a sand patch test. And then at each of these 12 sites, we did this 4 times. Each location was spaced about 100 feet apart. We were, in the end, get 12 British pendulum tests at each of the 12 sites, along with 2 cores. We cored once in the wheel path and once in the center. And we were also able to get 1 polish test for the material that was used on this pavement section. This is a picture of some of the field work doing the British pendulum test out in the field. You can see the 2 wet dots where the British pendulum was conducted in the wheel path. We're right there next to live traffic. Here's a picture. You can see the sand patch test being performed here to calculate the mean texture depth. We're coring out in a lot of the locations. We had 2 locations on I-15, 3 locations on I-70. We had some up in Tooele, West Valley, Draper. This is a picture that's, let's see, on I-15, down at milepost 188. And you can see we tried to pick the locations that were representative. We had to avoid cracks, we had to avoid sealants. The British pendulum test and the skid path, because it was 80 feet long, we had to choose the most representative sections of road that we could find. It couldn't be curved, it couldn't be have a slope on it either. One of the interesting findings that came out of this research was, as we were measuring the temperature on all these different locations, we found that there was a trend. As the temperature increased, our friction values also increased. And this has something to do with the decrease. This has something to do with the softening of the rubber. As it heats up, the rubber becomes softer versus when it's cold, it's more rigid, and it creates a higher friction value. And so we think this is a great finding, and it's something that may be able to be incorporated by UDOT as they use their skid trailer, that maybe there could be a temperature-type monitoring device on the back of it. And there are some states that do this, that do record the temperature before they do the skid testing. So what did we find for the first objective? Correlating the field friction number from the skid trailer to the British pendulum out in the field also. We found a great correlation. We got R-squared value of 0.81, and as you can see up there, it's a pretty good correlation. This is something that has been performed previously in other states, and what we have found aligns greatly with what we found in Indiana, the DOT, and also the Texas DOT. Again, as the British pendulum values increase, we also found that the skid values increase. Now, this is important because with this equation, you're able to figure out say you have a location on the road that you're not able to get a skid trailer to, because the skid trailer needs to go for 40 miles an hour continuously. You can't have any steep slopes or curves. Now you're able to take a British pendulum out to the field, these difficult-to-reach locations, perform a test, and then correlate to see what would the skid trailer number be if we also performed a test in this location. So how do we do on objective number 2? Comparing the laboratory polish values with the British pendulum values that were out in the field. We felt we did pretty good on this. We got R-squared value of 0.63, not as high as previously, but we felt that this may be due to the fact that the polish value represents end of life, and the pavements that we tested were not at end of life yet. They still had serviceability, and so we don't know where they were at on that deterioration curve. And so because of this, we think that's created some of the chatter, and it would be interesting for future studies to study what is the rate of deterioration of these aggregates. How do they polish? How fast do they polish? Are some better than others? For objective number 3, which is really the objective that started this whole thing back in 1996 when UDOT was comparing their 32 chip seal sections. And they took the skid trailer out to these sections and they performed laboratory testing. And they didn't have a correlation. You kind of saw that scatter. Well, when we were able to perform this on our 12 different sites, we found that there was a correlation came forth. And it makes sense. The lower the polish value has in the lab, the lower the field friction has from the skid trailer. Now, this is good to see. This is more statistically adequate. This is more defendable. This is hopefully a new basis that UDOT can take their friction management program from. And so we were excited to see this data. And now you have the ability to take an aggregate before it's even placed on the field and understand how it will perform. You're able to have confidence that the laboratory values that you're getting from your polish value will keep your public safe out on the road. Another thing you're able to look at now is, how does that 31 fare? What would the current UDOT standard specification says you have to have 31 or higher. And we found that a 31 or higher correlated to about a 45 out in the field or higher. And this is great news, seeing how the threshold, the trigger value on roads right now is about 35. And maybe the contractors might like to see this because, well, maybe there's some wiggle room. Maybe if you bumped it down to 30, 29, could you still use those values? So this opens up a new kind of a way to provide some engineering judgment to those borderline type materials that you're seeing out there. I know a lot of times when clients come to Robert Kistner to perform a polish test, sometimes they have borderline material and they just feel like there's nothing they can do about it. So this shows that maybe there might be opportunities to open up new sources that have previously been excluded because their polish value has failed. So overall, how do we do on our research objectives? We felt we did pretty good. We got R-squared values that were pretty high. Again, the laboratory and the British pendulum wasn't as great, but we think this is because there's a deterioration trend over time with all aggregates. And because the polish value in the lab is so aggressive at 10 hours, we would think that that's not exactly equivalent to what we're finding out in the field at 8, 9, 10 years. So how could we improve upon that? Well, you can actually take the test from the accelerated polish machine at different increments. You can take it at 0, 2, 4, 6, 8, 10 increments, and you can actually get a curve and a trend. So this is something that we thought maybe add value to UDOT's current approach. That way you're able to kind of get a time history of deterioration and then more adequately match it to the existing age of the pavement that's out in the field. So future research, like I've been saying, friction deterioration curves. I really think that understanding the personality of your aggregates. As we were doing this study, we found that some aggregates in southern Utah that were more volcanic in nature and they were more porous, they actually didn't deteriorate over those 10 hours of polishing. They started with a polish value around 36 and they maintained that. And that's because as they wore down, instead of polishing, little pieces popped out and almost rejuvenated that surface. So we actually found that there are aggregates in Utah that are kind of almost immune to the polishing effects of tires, which would be great aggregates to use if you needed a high friction surface course. There's other aggregates, typically those with limestone and dolomite in them, that polished very fast. And you could see as we took it off the wheel at those different increments that there was a steep decline right off the beginning, and then it kind of leveled out way below, like a 24, way below the 31 value. Some future research should look into how does the temperature affect these friction tests, and do we need to normalize the tests for temperature so we can get more adequate and reduce the variability throughout the day. As you know, the temperatures can swing from 60 degrees in the morning to 120 degrees in the middle of the day in Region 4. How does this affect the friction? The data that we have, we kind of dived into that, and we found that there are correlations that could be applied to the friction values. And also tire wear. There was one section where the tire reached end of life when we were out into the field. We were able to skid a section of road with an old tire, and then we skidded that section as soon as the new tire was put on. And we found that the difference between an old and a new tire was 1 or 2 points. And so taking that into consideration could also help. Tire pressure. We found that earlier in the morning the tires were a little bit lower than at the end of the day, and they typically needed a warm-up period. Most exciting thing that we can do now is look at other methods of testing friction and texture. The British pendulum is a great device. It's been around forever. It's used throughout the world. The correlations that it has with other sites are great, but there's new devices coming online now. The Japanese have recently made a device called the Dynamic Friction Tester, the DFT, and it's a spinning device that tests the friction, and it's portable and go out in the field just like the British pendulum. British pendulum swings at the rate that gravity pulls the pendulum down, which is one speed, about 15 to 20 kilometers an hour. but that's not typically the speed that the traffic is. It's not even typical of the speed that the friction trailer pulls at 40 miles an hour. The neat thing about the DFT is it spins it can go up to 90 kilometers an hour and continuously read what that friction is at all these different speeds. The circular texture meter, it's a laser texturing measuring device. It goes over the same footprint as the DFT, and it measures the texture with a laser as it goes around. It gets you very accurate texture readings. And with these two instruments combined, you're able to get an International Friction Index number. The neat thing about this number is it can harmonize with a lot of other different tests. Federal government doesn't dictate how states test for friction. It's up to the state to choose and create their own friction management program. And this has led to a variety of testing methods through all these different states. The great thing about an International Friction Index number is it now can harmonize with any other state that uses a DFT or a CFTM. We were able to actually recently get a grant from the FHWA. UDOT applied for a loan to borrow a DFT and a CTM machine. And just this last summer, it came to UDOT, and we were able to take those two machines out to those 12 different sites and measure the friction and the texture again with these new machines. And so that's for an additional research project, but that was something that we were able to do just this last summer. It was a benefit that was provided by the FHWA for free. They actually flew the equipment in. They flew someone in from Penn State to train us how to use this equipment. And we learned a tremendous amount about friction. We learned about how other states do it. And it was just a great collaboration between a DOT here in Utah and the FHWA. And so I've been excited about this research. We found some interesting things. We think there's room to grow, to keep understanding friction. We feel that now that with this information, there's a more statistically adequate basis for the determinations that UDOT's using for their specifications. And we feel that it's more defendable and it's more reliable and a confidence building. And now it gives you some wiggle room for engineers and contractors to come together and to make engineering judgment calls about the material that they have. There's not just one way to evaluate the aggregates that you have. And this was the topic that we're interested in. We're continue going forward. We got more research planned up. We're now starting studying the mineralogy of the aggregates. We've gotten samples of these different locations, and we're starting to look at them under scanning electron microprobes, understand the mineralogy and see if there's a way that UDOT can look at the different quarries at a mineralogical level and see how well that correlates to pavement friction, things like that. So this is kind of where we're at. I was just take any questions right now, or we could save questions for the end. I guess we got a minute or two for questions, so feel free.
What was the difference, correlation between like an open graded and an SMA?
That's a great question. The main difference was in their texture. When we did the sand patch test and then when we did the circular texture meter, we found that the chip seals, the open grade friction courses, they were very aggressive, and the SMAs, they had less texture. And as far as friction goes, the SMAs are actually a little bit lower. The best sites that had the highest friction were open graded friction courses, and your SMAs were significantly lower. One interesting spot that we found was near Salina, and it's actually a road in between the coal, where they mine for coal, and the power plant. And trucks, nonstop, day and night, go over this SMA section. And they have worn that so smooth, it actually had the lowest friction that we tested on this whole research study. And so I think there is a need to understand that there are different levels of friction from the surface treatments that you choose. And that was another study that we started looking at. We wanted to look into what surface treatments provide the best friction for the lowest cost. That wasn't in the scope of this research project, but that is something that we've looked into. But SMA is typically on the lower end when it comes to friction values compared to microsurfacing and open graded surface cores. Oh, one more? Mm-hmm. So that's a great point. We actually had someone ask us that question from New York. They wanted to use some glass aggregate as a high friction surface course. The reason being is you could paint black underneath this clear aggregate, or any color. You could see through the glass aggregate the color that you painted below it. But the problem is it seemed risky, glass aggregate, And so what they did is they created a board. They put some epoxy on the board, the small 2-foot by 2-foot board, and then they applied their glass aggregate to that. They sent us the board, and we were able to strike the board with the British pendulum in the laboratory to see what the friction in the laboratory would be. Then using these equations, we were able to predict what the skid trailer value would be if this was applied into the field. And that's something the DOTs need to know. Texas would not let this firm apply glass aggregate to their road without having some kind of confidence that it would perform well. And so we were able to provide them this information, then TxDOT granted them access to at least put it on their shoulders for now, this glass aggregate. And so what do you need for these high-friction surface courses? A 2-foot by 2-foot sample, bring it to the lab, and we can evaluate what the lab would be, and then we could estimate what the field friction would also be if this was performed in the field. All right, thank you.